In this video, we will look at uniform continuity, which is a stronger form of continuity than the regular plain old continuity. We will start by reviewing what it is for a function f to be continuous at a point C. We will then extend that and look at what it is for a function f to be continuous on a set D. And then we will define what it is for a function to be uniformly continuous on a domain, a set D. We will look at a strategy for proving uniform continuity, and we will look at a theorem which, to summarize this and the theorem, we have that uniform continuity implies continuity on D, and continuity on a compact D implies uniform continuity. Then we will look at Cauchy sequences. We'll review the definitions and also the Cauchy Convergence Criteria theorem so that we can come to this theorem that says if we have a function that's uniformly continuous on D, then a Cauchy sequence will map to Cauchy sequences. Finally, we will learn how to extend a function, and that'll be another way we can tell if a function is uniformly continuous. And to comment on this last theorem, sometimes things at the very end of the book, like by then I'm tired of reading the chapter, and I figure maybe since this is at the end of the chapter, it won't be on the test anyway. This theorem is actually quite useful, and it's very easy to use. So don't skip through it, even though it's at the end. To start our definition of uniform continuity, we will just start by reviewing the definition of continuity. So if we have a function from some domain to R, and C is in our domain, we say f is continuous at the point C if for every epsilon there exists a delta such that x minus c is less than delta, implies that f of x minus f of c is less than epsilon. We hadn't emphasized the definition of what it is for a function to be continuous on a set, or f to be continuous on a domain D. But it's important now that we're talking about uniform continuity that we understand this definition better. So to be continuous on a set D, or on a domain, for every element C in the set D, and for every epsilon greater than 0, we can find, or there exists, a delta greater than 0, such that whenever the absolute value of x minus c is less than delta, then f of x minus f of c is less than epsilon. And it is worth noting for this definition, for every different element, C and D, we can have a different delta. And that is an important thing to note because that is exactly what sets a uniform continuous function apart from a function that is just continuous. If it happens that there's a single delta that can be found that will work for all C, then the function is said to be uniformly continuous. And we say f is uniformly continuous on a domain D. And this definition is what we use for proofs. So f is uniformly continuous on D if for every epsilon there exists a delta such that x minus y, the absolute value of x minus y is less than delta, implies that the absolute value of f of x minus f of y is less than epsilon. We will do an example in another minute that will give us more insight into what it is to be continuous versus uniformly continuous. It is worth taking the time to compare the definition of a continuous function f continuous at a point C versus f continuous on a domain D, recalling that delta can vary for each C, and then this definition of uniformly continuous. They all look very similar, but it's good to take a look at that. And one other point, while it is proper to speak of a function being continuous at a point, uniform continuity is a property that applies to a function on a set, like on a set D, a domain. We never speak of a function being uniformly continuous at a point. While it's proper to speak of a function being continuous at a point, like a point C, uniform continuity is a property that applies to a function on a set, on a domain. So we talk about continuous at a point C, uniformly continuous on a domain or a set D. We never speak of a function being uniformly continuous at a point. And we have this proof strategy. We're going to reduce the inequality f of x minus f of y to be less than epsilon to something that looks like the form x minus y is equal to something in terms of epsilon. and then we're going to plug our epsilon and our delta, or I'm sorry, we're going to plug our delta into this proof template. I'm going to now use this proof strategy to prove that the function f of x equals 2x is uniformly continuous on R. I will start by looking at f of x minus f of y is less than epsilon, this part of my proof template. So I'm going to plug in 2x for f of x and 2y for f of y, set that less than epsilon. I can factor out my 2, and I have 2 times x minus y is less than epsilon. So this is where I have something of the form, my x minus y equals something in terms of epsilon. Actually, I need to move this 2 over, so I have something in terms of epsilon. And here I divided everything by 2, so I have exactly this form, x minus y is equal to something in terms of epsilon. So now I'm going to let delta equal to epsilon over 2, and next I'm going to plug this delta into my proof template. And what I get is my proof, given epsilon greater than 0, take delta equal to epsilon over 2. Then notice whenever x minus y is less than delta, and now I'm going to plug all this stuff in backwards. X minus y is less than epsilon over 2. Multiply everything by 2. 2 times x minus y is less than epsilon, and then 2x minus 2y is less than epsilon, which gives me exactly what I wanted to show, which was that whenever x minus y is less than delta, and here I have x minus y is less than delta, then my f of x minus f of y is less than epsilon, which I have right here, and therefore f of x equals 2x is uniformly continuous on R. Next example, I am going to write the negation of the definition of uniform continuity. So I have my negation here, and inside here I have my criteria or my definition of uniform continuous, which is right over here. So translating this, for every epsilon greater than 0, so here I have for all epsilon greater than 0, there exists a delta greater than 0, there exists delta greater than 0, such that f of x minus f of y less than epsilon whenever x minus y is less than delta. So in other words, if I have this condition, then I have f of x minus f of y is less than epsilon. So, and this is for all x and y and d. So for all x, y, and d, if x minus y is less than delta, then f of x minus f of y is less than epsilon. So this is what I want to negate. And I start by, when I do the negation, my for alls become there exists, and my there exists becomes for all. And here, so I moved in my negation, and so then I stopped over here at this part, and I still want to negate for all x, y, and then I left the rest of my conditional here. I went ahead and converted my for alls into there exists, and then I needed to negate what's here, and to negate the conditional, I take my hypothesis, my x minus y is less than d, and I AND it with the negative of my conclusion. So the negative of my conclusion is f of x minus f of y is greater than or equal to epsilon. And now this is really important. And when you talked about uniform continuity, you had to prove something for all x and y. And by the time you want to prove something is not uniformly continuous, you only have to find an x and a y. You don't prove it for all. In fact, just one example will do. And again, that's because when you negate, the for alls become there exists, and vice versa. The there exists becomes for all. For an example of using our negation of the definition of uniformly continuous, we're going to prove that the function f of x equals x squared is not uniformly continuous. And this is also a good example of actually what it means to be uniformly continuous, because we'll have a counterexample and we'll do a graph to give us some more clarity on the definition. I have also written for your reference our negation of the definition of uniformly continuous. We can get some intuition on why f of x equals x squared is not uniformly continuous by doing a graph, and it'll also give us more insight into what it means to be uniformly continuous. So looking at this graph here, I have graphed f of x equals x squared, and I have the point 1, 1, and I have the point 2, 4 over here. You can see as x gets larger and y gets larger, for a given epsilon, and here at 1, I use the epsilon of 1. So I have 1 plus epsilon and 1 minus epsilon. And then here for the point 4, Again, I use the same epsilon 1, so I have 4 plus epsilon and 4 minus epsilon in here. But for a given epsilon, delta gets smaller. In other words, we don't have one delta that will satisfy this condition. It's like we were talking about, for f to be continuous, there exists a delta, but your delta might be different for each c, and in this case it is because it's not uniformly continuous. To start my proof, I'm going to look at f of x minus f of y. So in this case, f of x is equal to x squared, so my f of x minus f of y is equal to x squared minus y squared, which is equal to the absolute value of x plus y times absolute value of x minus y. We are going to start by letting epsilon equal 1, and any epsilon greater than 0 will work. The reason why we chose epsilon equals 1 is because it's a very easy number to work with, and why not choose an easy number? And looking at the negation of this definition, that means given any delta greater than 0, we need to show there exists an x and y. So we only need to find one set of values for x and y such that x minus y is less than delta, and f of x minus f of y is greater than or equal to epsilon, and in this case, epsilon is equal to 1. And this is the clever choosing of x and y, and epsilon equals 1. So for any x, let's let y equal to x plus delta over 2. So that way when we have the absolute value of x minus y, we have x, and then y will be x and delta over 2. So what we get is the absolute value of negative delta over 2, which is equal to delta over 2, and that is certainly less than delta. So we have this condition met here. And now we need to look at this last condition here, or this condition here. So we have f of x minus f of y, which is this absolute value of x plus y times absolute value of x minus y, and we want that to be greater than or equal to 1, which I have written backwards here. And we know that x minus y is equal to delta over 2. So we'll substitute this in for delta over 2. So now we have the equation 1 is less than or equal to x plus y times delta over 2. So in other words, absolute value of x plus y is greater than or equal to delta over 2. We will let x equal 1 over delta. Then our proof is let epsilon equal 1, given any delta greater than 0, let x equal to 1 plus delta, and y equal to, now we plug in for x, 1 plus delta over 2. Remember, we set y equal to x plus delta over 2. Now we have x minus y less than delta, and f of x minus f of y, which is equal to absolute value of x plus y times absolute value of x minus y, which is equal to 1 plus delta over 2, this is x, this is y, times an x minus y, we can plug in delta over 2. And then when we do the algebra, we will see that we have our f of x minus f of y is greater than 1, which again is our epsilon, and thus we've satisfied the condition, which I don't have here anymore, for not being uniformly continuous on R. And let's take one more look at what we had done. This was my definition for not continuous. Let epsilon equal to 0. Then we want to show, given any delta greater than 0, that we can find x and y such that these conditions hold. So here we have epsilon equal to 1, given any delta. We've chosen our x's and y's so that our x minus y is less than delta, but our f of x minus f of y is equal to 1, which is certainly greater than or equal to 1. Thus, f is not uniformly continuous on R. So I feel like there were three kind of clever parts of this proof, and the first one was when we did the negation of the definition of uniformly continuous, so we would have a criteria for not being uniformly continuous. The second one is when we looked at f of x minus f of y, we factored it into two parts, x plus y and x minus y. The third and then we said it's greater than or equal to 1. The third big thing that we did is we did a clever choice of x and y, because we were looking at how we were going to add x and y together versus what would happen when we subtracted x and y. So we wanted things to kind of cancel out and add together in clever ways. A remark about this example, which will lead us to the next theorem. The difficulty with f equals x squared, the difficulty with it being uniformly continuous, is that the x plus y, the absolute value of x plus y, got arbitrarily large. So if we restrict the domain to a compact set, then this cannot happen. For example, if we restricted D to be the closed interval, -5 to 5, then x plus y is going to be bound by 10. And then given epsilon equals 0, if delta is equal to epsilon over 10, and x minus y is less than delta, then we're going to have our f of x minus f of y, x squared minus y squared, we have that same factoring, but this now is going to be 10, and this will be delta, so we have 10 delta is equal to epsilon, so here we have epsilon is equal to, delta is equal to epsilon over 10, in which case we've shown that x squared is continuous on the interval -5 to 5. And this example of restricting the domain to a compact set is a special case of the next theorem. So our next theorem says if f is continuous on a compact set D, then f is uniformly continuous on D. The proof uses neighborhoods and open covers. So down here I have the relevant theorem that we will be using, and this is from the section or the chapter on continuity, the definition of continuity. So this theorem related continuity to sequences, neighborhoods, and accumulation points. The part we're going to use is the one about neighborhoods. So f is continuous at C if and only if for every neighborhood V of f of C, there exists a neighborhood U of C such that f of U intersect with the domain is a subset of V. So in other words, here we have f of C and V is our neighborhood. So if we have our neighborhood around f of C, if it were continuous at f of C, that means down here in the domain, we should have a neighborhood U that when we intersect it with the domain, the image of this will be completely contained in V. Using this theorem here, we're going to start with given any epsilon greater than 0. Since f is continuous on D, it's continuous on the set D, then f is continuous at each element x in D, and for each element x in D, there exists a delta x greater than 0. And remember here, we had mentioned that every element in D might have a different delta. That's why we have to put delta x, and such that f of x minus f of y is less than epsilon over 2. So if someone gives you epsilon, we can certainly find a different delta for epsilon over 2 whenever x minus y is less than delta x and y is an element of D. Now I have the family of neighborhoods, my script f for family, of the neighborhoods x, so it's centered around x, with a radius of delta x over 2 for x and D is an open cover. And since D is compact, that means f contains a finite subcover, that is x1, x2 up to xn in D. Given those neighborhoods, we have a finite subcover. So this is our neighborhoods for x1 up to xn, and they completely contain D. If we let delta equal the minimum of our delta x1 divided by 2 up to delta xn divided by 2, we claim that this delta proves uniform continuity in our domain D. So now that n x of I is an open cover, that means when we choose our x and y and delta, such that x minus y is less than delta, then for each of our x has to belong to one of these neighborhoods because the set of these neighborhoods is an open cover. So here we have x and y, and the point is that this x, even if it's not one that was one of the finite ones used to generate an a finite subcover, that it will be in one of these neighborhoods that is part of our finite subcover. And this is the part we're going to use in our next slide from this drawing. So since x and y are here, they have to be within delta x sub I, the radius of our neighborhood, delta x sub I over 2. Now we have x minus y is less than delta, which is less than or equal to delta x sub I over 2 because delta was chosen to be the minimum of the radius of our neighborhoods. Then we have y minus x sub I is less than And here we just took this and we added and subtracted x in the middle, and then we separated out the two absolute values. So we have y minus x, which is less than delta x sub I over 2, plus x minus x sub I, which is less than or equal to delta x sub I over 2. So these two together added gives us delta x sub I. So from there we have f of x minus f of x sub I is less than epsilon over 2. So it follows that f of x minus f of y, if I just add an f of xi and subtract an f of xi, I can divide it into these two inequalities, will be less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. And that's exactly what we needed to prove continuity. So with this theorem, we can summarize everything else like this. Uniform continuity implies continuity on D. Continuity on a compact D implies uniform continuity. But in general, continuity on D does not imply uniform continuity. And just to kind of look at this one more time. So uniform continuity implies continuity on D because uniform continuity is a strong form of continuity. If you look at this definition, to be continuous on D, you just have to be able to find a delta for every C, and it can be a different delta for every element in D. But to be uniformly continuous, you have to have a single delta that works for all of your elements in D. So in that way, uniform continuity is a stronger form. It requires more. Also, when I said continuity on a compact domain implies uniform continuity, but in general continuity on D does not imply uniform continuity, again, that's because continuity on D allows for different deltas for every element in D, whereas uniform continuity has more requirements in that it has to be a single delta that satisfies every element in D. Our next theorem involves Cauchy sequences, so we're going to review the definition of a Cauchy sequence, the informal and a formal definition, as well as review the Cauchy convergence criteria and do a quick example. When a sequence is convergent, not only do the terms get close to the value of the limit for large n, but also they start to get close to each other. So getting close together is called the Cauchy property. So the formal definition of a Cauchy sequence is if you have a sequence of real numbers, it is said to be Cauchy if for each epsilon greater than 0, there exists a natural number capital N such that m and n greater than or equal to capital N implies the distance between Sn and Sm is less than epsilon. So the idea is if you go far out enough in the sequence, eventually the distance between Sn and Sm can be set arbitrarily small. So no matter what epsilon you choose, you can go out far enough such that all elements the distance between all elements is smaller than epsilon. And when we looked at Cauchy sequences, when we were looking at sequences, we also had this Cauchy convergence criteria that said a sequence of real numbers is convergent if and only if it is a Cauchy sequence. So for our example, we want to find a continuous function and a Cauchy sequence, xn in D, such that f of xn is divergent. We will start with the continuous function f. So we're going to define f on the open interval 0 to infinity, and f of x is equal to 1 over x. And again, since it's the open interval, it does not include the point 0. So we're continuous all through D. We are going to propose xn, our sequence, to be 1 over n. So we know the limit of 1 over n is equal to 0, so it does converge, and therefore, by our Cauchy convergence criteria theorem, it is a Cauchy sequence. Now when we look at f of xn, that's equal to n, and this sequence diverges. It goes to infinity as n goes to infinity. Our next theorem tells us that uniform continuous functions map Cauchy sequences into Cauchy sequences. So if you have a function from D to R that is uniformly continuous on D, and you have a sequence x of n, which is a Cauchy sequence, then f of xn is also a Cauchy sequence. For our proof, we're going to start given epsilon greater than 0. Since f is uniformly continuous on D, that implies there exists a delta greater than 0 such that we know from the definition of uniformly continuous that that implies the absolute value of f of x minus f of y is less than epsilon whenever absolute value of x minus y is less than delta. And since xn is Cauchy, we know from our definition of a Cauchy sequence that there exists an integer capital N such that the absolute value of xn minus xm is less than delta whenever n and m are greater than capital N. Now, if you notice that xn minus xm is less than delta is the same as x minus y is less than delta. In other words, xn and xm are particular examples of x and y. So now, over here in this part of this definition of uniformly continuous, I can plug in xn for x and xm for y. And that is exactly what I have done here. So I have the distance between f of xn and f of xm is less than epsilon, which makes f of xn a Cauchy sequence. And we are done with our proof. Our next theorem tells us that a function is uniform continuous if and only if an extension is continuous. So in particular, and you do need to know the particulars, a function f going from the open interval ab is uniformly continuous on the open interval if and only if it can be extended to a function f tilde that is continuous on the closed interval. So if it's uniformly continuous on the open interval, if the extension is continuous on the closed interval. And this theorem is quite useful because it gives us another way of determining if a function is uniformly continuous. Before we do this proof, let's take a moment to look at what this f tilde is equal to. So on the open interval between a and b, f of x tilde is just equal to f of x. The only thing we need to do now is extend f of x on the endpoints a and b, and we're just going to set that equal to the limit as x approaches a of f of x, and the limit of f of x as x approaches b, which is the natural extension. And I'm going to start the proof proving the opposite direction. That is, we're going to assume we have a function f tilde that's continuous on the closed interval ab, and we're going to show the function f on the open interval is uniformly continuous. So if f can be extended to a function f tilde that is continuous on the compact set ab, then f tilde is uniformly continuous. By the continuous on a compact set implies uniform continuity theorem, which is stated right here. It says that if a function is continuous on a compact set, then it is uniformly continuous on that set D. So if f bar is continuous on the closed interval, and the closed interval, because it contains its boundary, is compact, then f bar is uniformly continuous. By the way, you know these names, compact set implies uniform continuity theorem, those are names that I just kind of came up with because I needed to refer to them. Some famous theorems have names, but even the non-famous ones, I thought we should kind of name them. Your book probably calls it something like 5.41 or something, but that doesn't mean much to me. It follows that f tilde is uniformly continuous on the open set AB, and hence f, which is just since f tilde is just an extension of f, by the time you get rid of the endpoints, f is exactly the same as f tilde. So f is also uniformly continuous on the open set AB. Now to prove the forward direction, that is, let's assume we have f, it's uniformly continuous on the open interval AB, and we want to show that the extended function f tilde is continuous on the closed interval AB. And our claim is that the limit as x approaches a of f of x and the limit as x approaches b of f of x both exist as real numbers. To remind you, these 2 points are important because that's how we're going to be defining f tilde at the endpoints a and b. So to see that these 2 limits exist, we're going to let Sn be the sequence in AB that converges to A. Then Sn is a Cauchy sequence because here we have the Cauchy Convergence Criteria, a sequence of real numbers is convergent if and only if it's a Cauchy sequence. So if Sn converges to A, that means Sn is a Cauchy sequence. So the theorem, the uniform continuity and sequences theorem, which is here, implies that f of Sn is also a Cauchy sequence. That's because this says that if it's uniformly continuous, then a Cauchy sequence gets mapped into a Cauchy sequence. So that's exactly what's going on over here. So this sequence, f of Sn, also converges to some real number, let's say p, which is going to be the limit as x approaches a of f of x, which we'll define to be p. Similarly, we can show that the limit as x approaches b of f of x is equal to some number q. And now we can define our f tilde. It's equal to f of x on the open interval ab, and then we have it defined at the endpoints a and b as the limit as x approaches f of x. So f tilde will be an extension of f, and since f is continuous on the open interval, then f tilde will also be continuous on the open interval. But f is also continuous on the endpoints ab, and therefore it is continuous on the closed interval ab. An example of this extension theorem is to determine whether or not the function f of x is equal to sine of 1 over x is uniformly continuous on the open interval 0 to 1 over pi. We will start by defining f tilde of x, which is equal to f of x when x is in the open interval a and b. So in this case, we have f of x is equal to sine of 1 over x when x is between 0 and 1 over pi. And then if x is equal to a, in this case the endpoint is 0, then we have f tilde of x equal to the limit as x approaches a of f of x. So that's the limit as x approaches 0 of sine of 1 over x. Similarly, we have this defined for b. But notice this limit does not exist since 1 over x is not defined for x equals 0. Since the limit as x approaches 0 of sine of 1 over x does not exist, f cannot be extended to a function that's continuous on the closed interval. And then by our extension of a function theorem here, it says that the function is continuous on the open interval if and only if it can be extended to a function that's continuous on a closed interval. Since it cannot be extended to a function that is continuous on the closed interval, that means the open interval, f on the open interval, is not uniformly continuous. Another example is to use the extension theorem to determine whether or not the function f of x is equal to x squared minus 4 divided by x minus 2 is uniformly continuous on the open interval 2, 4. I started by factoring my numerator so I could cancel with my denominator here, and I give f of x is algebraically equivalent to x plus 2. But you can see that x minus 2 was problematic at the endpoint 2. So I can define my extension, f tilde of x equal to x squared minus 4, x minus 2, which is essentially f of x, when x is between 2 and 4. At the endpoints 2 and 4, I'm going to define it as the limit for the endpoint x equals 2, the limit as x approaches 2 of x plus 2, which is equal to 4. And then for my endpoint x equals 4, that's the limit as x approaches 4 of x plus 2, which is equal to 6. So this, if I plot it out, you can see that it is continuous. And since f can be extended to a continuous function, f tilde, on the closed interval 2, 4, by the extension of a function theorem, f is uniformly continuous on the open interval 2, 4. We have covered the definition of a function being continuous at a point, of a function being continuous on a set, and then a function being uniformly continuous on a set. We looked at strategies to prove uniform continuity. We looked at the theorem that continuous on a compact set implies uniformly continuous, which means that uniform continuity implies continuity on D, and continuity on a compact D implies uniform continuity. We also looked at Cauchy sequences so we could get the uniform continuity and how it relates to Cauchy sequences. And finally, we looked at extensions of a function and how we can use extensions of a function to determine if a function is uniformly continuous. I have these problems for you to try. Pause the video, give them a try, and actually on the next slide, I have a hint for problem number 2. And then following that slide, I have solutions. So here is my hint for problem number 2. And these are the solutions for the first 2 problems. And here is the proof for the last problem. And that's it for this video. Thank you for watching.